Welcome to another video. I fortunately got this question today in an email and I was excited because I've been looking forward to solving a problem like this, although this one requires some technicalities. Okay, let me read the question to you, then we're going to try solving it together. The question is to find all 4-digit numbers. So this is how you write a 4-digit number. So it is not A times B times C times D. It is just these are the digits and that bar on top is holding the letters in place. So we can say this is like A1000, B100, and CTD, right? That's how we read it. So we're looking for all 4-digit numbers such that if you take the square root of this number and you divide it by, if you form a number using the first 2 digits, add it to the number you form by the second 2 digits, and then the next 2 digits, and you take the square roots of those individual numbers, the answer you get is going to be rational on the assumption, again, that A and C are not zeros. Because if A is 0, then this is not a 4-digit number. And if C is 0, then this is not a 2-digit number, and this is not a 2-digit. So we're just trying to block all the holes in the question. So how many of these kinds of numbers exist? I already told you in the past, whenever you get a question saying find all, it is either all of them are the same thing, or there is just one of them that behaves like that, or even if it is not one, maybe 1 or 2 or 3, but at least you can count them on your fingers. Or there's a general pattern to find all of them. Let's get into the video. Essentially, we're looking for this. This is an example. 1, 2, 3, 4. You take the square root of 1,234 and you divide it by the square root of 12 plus the square root of 34. And the answer you get is not irrational, it is a rational number. Looking at this, that's not possible because 1, 2, 3, 4, firstly, is irrational. I mean, the square root of 1, 2, 3, 4 is irrational because this is not a perfect square. That's 1. 2, this is not a perfect square. That's irrational. This is not a perfect square. And there's even a bigger problem. Let's say you can simplify rad 12. You're going to get the square root of, you're going to have 2 rad 3. You cannot simplify rad 34. Now look, this is rad 34, this is rad 3. These two radicals are not in the same field, which means you cannot add them together. And because you can't add these two together, even if this is a perfect square and you get a nice number, this is going to be a problem. In fact, even if this was something like, let's say 27 rad 3, you see, and you have this 2 rad 3 plus rad 34. Let's say this is not the same. I'm just giving you an example. If this was not there, these two can cancel each other. And if this was not rad 3, if it was not 34, if it was rad 3, we could add these two together. We get 3 rad 3, and then the 2 rad 3s will cancel each other, and we're going to get a rational number. So if these two are not in the same field, that is, the radicals that come from simplifying them are not the same thing, then we cannot add them, we cannot simplify, and there will be no rational number. So for this question to even have an answer, these two must be in the same quadratic fields. So remember, the word field in math is just the term used to describe a set of numbers that can be added and multiplied such that the addition will still keep them in the same field. Okay? It's like adding 2 positive numbers will always be positive. That's an example of the property of a field. So that's important in this. Okay? Forget about the mathematical jargon that I'm just using. I just want you to know that these two must have the same radicals. Otherwise, you cannot even do anything to this sum. So it is either there are no radicals or they are the same radicals. So let's begin the journey, because this is the whole idea of solving this problem. So to begin the solution, it is better for us to give this AB a name. So we're going to say, let these two-digit number AB be equal to a giant X, and let CD be a giant Y. This is going to change everything. Now, what does ABCD mean? Look, it's like saying 1, 2, 3, 4. We've called this X. We've called this Y. But this number is 1,204. Is the same thing as saying 100 times 12 plus 34. That's the meaning of 1,234. 1,234. 1,200s and 34. That's what this is. So it means that this number ABCD is equal to 100 plus. That transformation alone has brought a lot of relief and less confusion. So the original question we have, okay, which I'm going to call Q. Let's call this Q. Okay, so therefore we have equals Q. We just need to find X and Y. So based on what I had explained before, if these two guys can be added together, they must be in the same quadratic field, or in algebra language, they must have the same radicals. Okay, so, but we don't know what the radicals are. But we know that when you take the square root of a number, it is either, if this is a perfect square, brilliant, you don't need to worry. But if it's not a perfect square, then the two of them must have the same radicals, so you can add them together. Otherwise, it can never be rational. Now, we don't know what those radicals are, so we're going to use some letter to represent the radicals. Okay, so we're going to say, let the square root of X be some number. Let's say it is A, B, C, D, E. We're already using A, B, C, D, so let's go R, S, T, U, V. Okay, let's call it R, rad, S. Okay, and let the square root of Y be R, S, T, rad, S. Okay, so we know, this is what I explained, okay, so I don't repeat it all the time. This is very important because now we can find X. Okay, if we find X, we just square both sides. Let's square both sides. So that means that X is equal to R squared S and Y equals T squared S. Now we go here and we go back to this original equation and say that this Q that we're looking for is the square root of 100 times X. But we said X now is R squared S. R squared S. Plus Y. What is Y? T squared S. T squared S. And we're going to divide it by this plus this, which is going to be R squared S plus T squared S. So we got R squared S plus T squared S. Oh, I thought it was going to be the sweeter version of it, but no. So now, if you look here, this is the square, this is S, this is S. If I factor out the S, I end up with the square root of S multiplied by the square root of 100 R squared plus T squared divided by the square root of S times R plus T. Ho, ho, ho. That's what Q is. This cancels this, so that Q is just the square root of 100 R squared plus T squared divided by R plus T. We're almost there. there are certain restrictions that r and t have. How do we know? Look, x is a 2-digit number. That means that r squared times s is a 2-digit number, and the biggest 2-digit number you can get is 99. So we know r squared s is less than or equal to 99 because x is a 2-digit number from our problem. That means the same thing. Where is that other guy? T squared s. T squared s is less than or equal to 99. That means that r squared is less than or equal to 99 over s, and t squared is less than or equal to 99 over s. I'm trying to create a restriction because that's how you get all your answers. It means that r squared is clearly less than 99. In fact, let's remove this. No, let's still leave it in case s is 1. What is the largest square that you have that is less than or equal to 99? That's 81. Yes. So that means r is less than or equal to 9. So r is less than or equal to 9, and t is less than or equal to 9. We have restricted all our options. So in order to find x and y, you just need to experiment with numbers from 9 all the way to 1. And you will get your answer. So we only have 9 numbers to try, okay? And that means if this is a rational number, this number here on top is not irrational. For this not to be irrational, it means when you take the square root of this number, you must get an integer. Since q is a rational number, then 100 r squared plus t squared is a perfect square, where k is an integer. K is the only way you will not get an irrational right now, despite all the things we've done, canceling out the radical and all that, is if what is under the square root sign is a perfect square. Well, look at this. 100 r squared plus t squared is the same thing as 110r squared plus t squared equals k squared. Where have we seen this before? It is in a village where Pythagoras was the scientist there. And that's it. So looking at this, this is a Pythagorean triple. They are the legs of a triangle. And according to the primitive nature of Pythagorean triples, if one of them is even, the other must be odd, which means this guy is odd, this guy is even. So when you want to test numbers less than 9, for this one, you don't need to test 2, 4, 6, and 8. You just need to test 1, 3, 5, 7, 9. Those are the numbers we test here. So how do we test it? We just want to see if we're going to have a number, test any number for r from 1 to 9, add it to this, see if it's going to be a perfect square. Okay, there are many methods to do this. You can use the Euclidean algorithm, but I just want to do a chart, do a table, and see what we get. 9. These are the possible values of r, because r can take up any number, but t will only take up the odd numbers. So the first thing we want to do is to compute 10r squared. Or, you know, 10r squared is the same thing as 100r squared. So let's write 100r squared. 1 squared is 1, 100, this is 100. Okay. This is 2 squared is 4, this is 400. 3 squared is 9, this is 900. 4 squared is 1,600. 5 squared is 2,500. 6 squared is 3,600. And blah, blah, blah. I did blah, blah, blah because I don't want to waste time on it. If you continue, you won't get the answer. The answer is within the first 6. So we now need to guess all the possible values of t that would make this a perfect square. So we do 1 squared would be 1. 101 is not a perfect square. 3 squared is 9. 109 is not a perfect square. Remember, we're adding, okay? 125 is not a perfect square. 149 is not a perfect square. 181 is not a perfect square. So r is not 1, and we couldn't find any t. So no solution for the first one. 1,601, not a perfect square, because you know that. 1,609, no. 1,625, no. 1,649, no. 1,681, yes. Okay, 1,681 is going to be 1,600 plus 81. That's 1,681, which is 41 squared. If you try this number, it doesn't work. This number doesn't work. No other number works. It's not a lot of work to do, but you can figure out that it's not a perfect square. So none of these other numbers work. No other number works. This is the only number that works. This is the 4-digit number we were looking for, and it is the square of 41. And as you can see, the first 2 numbers is a perfect square. The last 2 is a perfect square. And we're good. And every condition is satisfied. Now you would wonder, what was S? Well, S was 1. But I didn't want to claim that S was 1 from the beginning, but no matter what S was, we had to cancel it out, okay? And this had to stay as a 2-digit number. And you can see all that we did, how we ultimately got to that answer. So here we go. We can say that, and check. The square root of 1,681 divided by square root of 16 plus square root of 81 is equal to 41 over 4 plus 9, 13, which is a rational number. Check. Never stop learning. Those who stop learning, stop living. Bye-bye.